Hello everyone. Welcome to the part 2 of stochastic convergence. In part 1, we discussed three modes of stochastic convergence, namely uh, everywhere convergence, almost sure convergence, and convergence in probability. In this lesson, we will discuss two more types of convergence. uh, Convergence in distribution and convergence in mean. So let us look at the convergence in distribution, which is also called the weak convergence. Uh, it's called weak convergence because it is probably the weakest form of convergence out of the well-known or commonly used types of convergences. Unlike in others, uh, the sequence of random variables yn and y do not have to be defined on the sample space in this case. When we discussed almost sure convergence, we were looking at a sequence of uh, random variables, say yn, defined on the same sample space, and the limiting random variable y also have to be defined on the same sample space. The scenario was the same when we discuss or when we consider convergence in probability also, and similarly convergence everywhere. But in this case, we may be looking at uh, two different sample spaces. Uh, we are not going to look at the closeness of the random variables as n becomes large. What we are going to look at is the closeness of the distributions of yns and the distribution of y. Means we are going to consider the distribution of y1, distribution of y2, distribution of y3, and so on, and see whether those distributions are converging to the distribution of y, right? When we say distribution, here we can discuss, we can consider, generally, we can consider the cumulative distribution function because we can discuss about cumulative distribution function regardless of the type of the random variable, whether it is discrete or continuous, right? On the other hand, if you are dealing with continuous random variables, then we can also talk about the densities. But usually, the definition of the convergence in distribution uh, is specified in terms of the cumulative distribution function. So, cumulative distribution function of y1, cumulative distribution function of y2, and so on. And finally, the cumulative distribution function of y. If the cumulative distributions of y1, y2, y3, and so on are converging to the cumulative distribution function of yn, uh, at each continuity point, right? Especially in a discrete CDF, there are some discontinuity points, but we are looking at the convergence at uh, the points where the CDF is continuous, right? So let's look at the definition. The sequence yn converges to y in distribution if their cumulative distribution functions converge at every point where the limiting CDF is continuous. Right. So let's see what this means. Mathematically, this means we are looking at the limiting CDFs, right? So f and y is the CDF of capital Y subscript n. And what we look at is the limit as n goes to infinity. If the limit is equal to fy, where this f is uh, the cumulative distribution function of the random variable y, right? So if this happens for all simple y values where this fy is continuous, then we say that the sequence yn, the sequence of random variables yn converge to y in distribution, in distribution. So this is the notation to write down that the sequence yn converges to y in distribution. Yn arrow y, we write down d above y, above the arrow to show that it is in distribution, convergence in distribution. So let us look at a very famous application of this convergence. We are talking about a sequence of random variables and another particular random variable. And there is a very famous theorem called Central Limit Theorem. Central Limit Theorem. There are several versions of that. We are considering the very most basic version of the Central Limit Theorem here. So what does Central Limit Theorem say? Let capital X1 up to capital X2 up to a sequence, right? X1, X2, X3, and so on, be a sequence of independent and identically distributed random variables with each xi having the mean mu and each xi having the variance sigma square. Both are finite. We have to assume that mu and sigma square both are finite. That means they exist. So remember, this theorem is not going to be valid for some special situations where the mean is not defined. Like if the x's are coming from a Cauchy distribution, that this theorem will not be valid. But for most of the practical uh, situations, uh, this theorem will be valid because for most of the practically used random variables, mean and variance exist. So define a new random variable xn bar, xn bar or x bar n. That is the mean, sample mean of the first n random variables, first n observations, if you want, if you consider in terms of simple x1 up to simple xn, in that case observations, but here the first n random variables. So just consider x bar n to be 1 over n summation I from 1 to n xi. So that is the sample mean. Then let's consider a new random variable defined in terms of x bar n as zn. Zn. This n here actually is important because we are going to look at what happens to this quantity and this quantity when n goes to infinity. So here n denote the sample size. So this is the sample mean based on based on a sample of size n. Right. For example, x bar 1 will be just any xi here. X2 bar will be actually x1 bar will be just x1 because we are considering the first n observations. X2 bar will be x1 plus x2 divided by 2. X3 bar will be x1 plus x2 plus x3 divided by 3, like that. Right. So the n is important here. So based on x bar n, define Zn as xn bar minus mu divided by sigma over root n. Why are we considering this quantity? Because notice that because if expected value of xi is equal to mu and variance of xi is equal to sigma square, we can, and because x1 up to xn are independent, uh, we can show that actually expected value of x bar n is the same as expected value of any xi, which is equal to mu. We can easily prove that expected value of x bar n is equal to mu. And also we can show that the variance of x bar n is equal to sigma square over n. Sigma square over n. So what we are doing here is standardizing this quantity by taking away the mean of this quantity and dividing by the standard deviation of this quantity. Right. So Zn is the standardized xn bar defined as xn bar minus the mean of xn bar divided by the standard deviation of xn bar. Remember, variance of xn bar is equal to sigma square over n, and therefore standard deviation of n bar is equal to sigma over root n. So this central limit theorem says, so here Zn, you can see that is a sequence. You can talk about Z1, Z2, Z3, and so on. So the central limit theorem says this sequence of Zn converges to a some random variable Z in distribution, where the distribution of Z is standard normal. Right? So that's what this notation says. Sequence of Zn converges to a standard normal distribution in distribution. Right? So you can also say Zn converges to some Z where the distribution of Z is standard normal. Right? As n goes to infinity. So that's what the theorem is. It's a limit theorem. The limit we look at is when the sample size goes to infinity. Uh, I'm going to look at the proof of this theorem also at the same time here. Just for your completeness of this part, we will look at the proof of the central limit theorem. We are going to prove this theorem using the moment generating function technique. Right. So what I'm going to do is actually I'm going to derive the moment generating function of this Zn and let n go to infinity and see what happens to that moment generating function when n approaches infinity, and thereby we will be able to identify the distribution of Zn as n goes to infinity. Right. So for the proof, we are considering n of the n of those x1 up to x2, x3, and so on sequence of x's. To consider x bar n. So let x1 up to xn be independent and identically distributed random variables. Right. So they are independent of each other. They have the same distribution. We don't know the distribution of x1 up to xn. They all may have, for example, an exponential distribution. They all may have a gamma distribution. They all may have a Weibull distribution. They all may have a Poisson distribution, like that. Whatever, all have the same distribution. Uh, and suppose that their mean, right, is equal to mu and variance is equal to sigma square. Usually these quantities are unknown, but we just use some notations. So expected value of x1, expected value of x2, expected value of xn, they all will be the same. That will be mu. Similarly, variance of x1, variance of x2, variance of x3 will be the same, sigma square. Right. So now let us standardize each variable. Consider the standardized each variable yi. Yi is equal to xi minus the mean of xi divided by the standard deviation of xi. So that is actually the standardized xi. Right. Now because x1 up to xn are IID, y1 up to yn defined like this. So this is defined for I from 1 to n. So yi is coming from those will also be IID. In that case, each yi will have mean 0 and variance 1, and therefore the standard deviation 1. right? So expected value of yi is equal to 0 and variance of yi equal to 0. Now, what we are going to do is we are going to derive the moment generative function of this Zn. Zn is actually the standardized x bar n. So in order to find out the moment generative function of Zn, it's easy if we note that Zn can be written as in terms of y's like this. Zn is equal to, you can, if you multiply this previous Zn expression by root 10, you actually, if you multiply by n, whole thing up, numerator and denominator, you will get this expression. And you can easily see that is equal to this expression in terms of y. So Zn can be written as in terms of y1, y2, y3 up to yn, where each yi is independent of each other. And each yi has mean 0 and variance 1. Okay, so because they are independent and identically distributed, we can show that the moment generating function of Zn evaluated at some value t is equal to the moment generating function of any of these yi's evaluated at t over root 10 to the power n. Right. This is very easy to show using the properties of the moment generating function, which I have already discussed in a previous lesson. Right. I have shown several mathematical properties of the moment generating function. Right. So here, actually, I will remind you those things again. Right. So I will just write down on the side here. One thing is if, for example, x has a moment generative function, say mxt, right? The moment generative function. Then if y is equal to ax plus b, where a and b are constants, then we can show that we can write down the moment generative function of y in terms of the moment generative function of x like this, e to the power b t times mx evaluated at at, right? So that is one property. And also you can show that if, for example, x1, x2 up to say xn IID random variables, they all have the same moment generative function, say, for example, mxt. Right, x1 has mxt moment generative function, x2 has the moment generative function mxt because they are IID, their moment generative function is the same. So now let us look at, say, for example, S is equal to the sum of I from 1 to n xi. Then we can show that, the moment generating function of S evaluated at t is equal to the product of individual moment generating functions. But now because each has the same moment generating function, this will be equal to mx t to the power n. Right. So here we are using actually these two properties. Here we can write down this thing as summation I from 1 to n yi divided by root 10. Right. So here we have several random variables, summation of several random variables. Each has the same distribution because each yi had the same distribution. Yi divided by root 10 also had the same distribution. So they each of those will have the same moment generative function, right? So the moment generative function of yi divided by square root n is equal to the moment generating function of y evaluated at t over root n first. And then when you take the summation, and because these each has the same moment generative function, you will have finally nth power. because it's going to be the product of the moment-generating functions. So that's how we get this one. The moment-generating function of Zn evaluated at t is equal to the moment-generating function of y, where y here, my means the moment-generating function of any yi is denoted by my evaluated at t over root 10 to the power n. Right. So let's now go to the proof again. So to obtain myt over root 10, first we derive myt, right? We want to get myt. Actually, we are going to get it because we don't know the distribution of y, because we don't know the distribution of x also, x1 up to xn, we don't know. But we can get an approximate expression regardless of the distribution of x by considering the definition of the moment generating function and using the Taylor expansion, right? So what we really want is my evaluated at t over root 10, but we will first derive my at t, right? Remember, by definition, myt is equal to, that is the moment generating function of y evaluated at t, is equal to the expected value of e to the power simple t times capital yi. This yi is the random variable, t is a real. Right. Now, we will, before taking expected value, we will expand this thing in terms of using the Taylor series expansion. So therefore, let me consider this as a function of t. So let's say gt is equal to e to the power t times capital yi. Now let us expand this thing around t equal to 0. So expanding this thing around t equal to 0, we get the Taylor series. Gt is equal to g0 plus the first derivative of g evaluated at 0 times t, and then second derivative of g evaluated at 0, t square over factorial 2, and so on. This will be an infinite uh, series. But we can notice that because gt is equal to this expression, we can easily see that the kth derivative of this function evaluated at t is equal to yi to the power k, then e to the power t yi, because every time we take derivative, yi term will come to the front, and then this will be keeping the same. So you'll have yi to the power k, e to the power t yi. Right. So now what we want is actually the expected value of this expression here, right? Uh, okay, first of all, the kth derivative of g evaluated at t is equal to this one, but we need is the derivatives evaluated at 0. So therefore, you have to put t equal to 0. Therefore, kth derivative of g evaluated at 0 will be just yi to the power k, right? So this is that. So when you substitute these things in the gt function, you get this expression e to the power tyi is equal to 1 plus tyi and so on. Here I'm writing the expansion up to this here, and after that all the terms I'm going to put in a summation, because later on we can show that all those go to 0 as n goes to infinity. That's what we are going to look at. Right? We are going to see what happens to the moment generating function when n goes to infinity. So therefore, the moment generating function, remember the moment generating function is equal to the expected value of this quantity. So that is going to be one expected value of this whole thing is going to be 1 plus t times expected value of yi uh, plus t square over factorial 2 expected value of yi square plus and so on summation t to the power k divided by k factorial expected value of yi to the power k. So that's uh, the moment generating function of y. But remember, expected value of yi is equal to 0 for each I. And because the variance of yi is equal to 1, expected value of yi square is equal to 1 as well. because expected value of yi square is equal to variance of yi plus the expected value of yi whole thing square, right? So thereby you will get expected value of yi square is equal to 1. And we are not going to substitute quantities for this one. We are going to just leave it like that because it's going to go to 0 at the end, right? So we get the myt like this 1 plus t square over 2 because one term here, this term disappears uh, because expected value of y is equal to 0. So we get the second term here and then these terms. So what we really need is actually my evaluated at t over root 10. So from this one, we can easily get that expression by putting t over root 10 in place of t. So we get this expression, my evaluated at t over root 10 is equal to this expression, right? Now, as I mentioned earlier, we are going to now look at, because now you can see that n has come into the n has come to the expression. So now we can look at what happens to this expression when n goes to infinity. What we are going to show is that actually this quantity is going to be 0 when n goes to infinity, right? So here we are considering terms for k greater than or equal to 3, right? So actually, we can see that each of these terms, when k is greater than or equal to 3, you have a real number to the power k, then k factorial. And the important thing here is n to the power k over 2. This quantity is also just a constant. N to the power k over 2. When k is greater than or equal to 3, you have, for example, when k is equal to 3, you have n to the power 3 over 2. When k is equal to 4, you have n to the power 2, right? So 1 over that term. All those terms are actually smaller than 1 over n. And therefore, when n goes to infinity, all these terms are going to be will be going to 0 even faster than 1 over n as n goes to infinity, right? All these terms for k greater than or equal to 3 will go to 0 even faster than 1 over n as n goes to infinity. So that's what this simple O notation means, right? So there are several ways of explaining this simple notation, simple O notation or little O notation. So I have just written down some of those ways of expressing that. So where O within bracket 1 or simple O, there is a big O also. Here we are using little O. O within bracket 1 over n denotes the term whose ratio to 1 over n tends to 0 as n goes to infinity. That means whatever the terms here, right? Uh, for example, suppose that term is denoted by Rn, right? So we are writing this quantity here. No? So suppose that is Rn. So Rn divided by 1 over n will go to 0 as n goes to infinity. So that's what another way of expressing this little o notation, right? So therefore, this whole thing is going to be uh, going to 0 faster than 1 over n as n goes to 0. Therefore, this whole thing can be written as a simple o or little o within bracket n. Right. 1 over n to the power k over 2 is also a simple o within bracket 1 over n. This whole thing is therefore, it's like a uh, sum of some constant times 1 over simple o or little o 1 over n terms. That's again going to be a little o 1 over n term because that term is going to go to 0 faster than 1 over n. Right. So therefore, we can finally write down myt over root 10 as 1 plus t square over 2n plus this term which goes to 0 very fast as n goes to infinity, right? So therefore, mz and t will be the nth power of this, right? So what we want is the limit of this thing as n goes to infinity. So here we are going to use a very standard limit uh, expression, from that, using that, we can show that limit of mzt is equal to e to the power t square 2. This is coming from the standard limit result. What is that limit result? The limit as n goes to infinity, 1 plus a over n plus a little o1 over n to the power n is equal to e to the power a. Right? So there is a standard limit result like that. So if we apply this one, and take the limit of these things here, it's like 1 plus, this is like a over n plus little o1 over to the power n. So directly applying this result, we can show that as n goes to infinity, m z n t is equal to e to the power t over 2. But actually, we know that, or we can find out from the standard books, that this is the moment generating function of a standard normal random variable, right? It is the same as the moment generating function of a standard normal random variable. That means a random variable whose distribution is standard normal, right? So you know that the moment generating function is a unique function for a given distribution. So therefore, uh, because the moment generating function of m Zn as n goes to infinity is equal to the moment generating function of the standard normal distribution. That implies, by the uniqueness of the moment generating function, that when n goes to infinity, the distribution of Zn converges to the standard normal distribution. Right. So that is the proof of the central limit theorem. So we can say that Zn converges to some standard normal random variable in distribution. Zn converges to a standard normal random variable in distribution. In other words, the distribution of Zn converges to the standard normal distribution as n goes to infinity. So therefore, we can write down it in this way also. So that is the proof of the central limit theorem. This is a very, very useful theorem, and it is used in various places in statistics, especially when we talk about large sample inference, right? Large sample inference. So the theorem is actually concerning the standardized sample mean, the distribution of the standardized sample mean uh, when n goes to infinity. But of course, practically, we don't have situations where n is infinite. What we are applying it for is actually when n is large. So according to the theorem, when n goes to infinity, the standardized sample mean will have a standard normal distribution. So, but practically what we take is when n is large, the standardized sample mean will be approximately normally distributed. Standardized, approximately standard normal. That's what the application is, right? When n is large enough, standardized sample mean will have a standard normal distribution approximately. So that's what we will be using, right? So let me tell it again. The application of central limit theorem is that when n is large enough, the standardized sample mean will have the standard normal distribution approximately. Approximately. In other words, the approximate distribution of the standardized sample mean will be standard normal if the sample size is large enough, right? So here the expression when or if the sample size is large enough is very important, because there is no particular rule saying that how large n should be for this to be valid, right? People usually consider this theorem to be valid when the sample size is greater than or equal to 30. But actually, you have to be careful when you are applying this because that's not a standard theorem or something, right? Even though the theorem may be valid when n is greater than or equal to 30 for a lot of situations, there can be situations where uh, the the distribution of the standardized sample mean is far away from the very far away from the standard normal distribution, even if n is equal to 30 or even 40, even 50, right? Sometimes we may need n to be like 100 or even more for this theorem to be valid, right? Especially if the distributions of x1 up to x1, x2, x3, and so on that we are considering the original random variables have a skewed distribution, very skewed distribution, then the central limit theorem will not be valid even if n is equal to 30. Even if n is equal to 40, it may not be valid, right? So you may require n equal to maybe 50 or 60, even 100 for the central limit theorem to be valid. On the other hand, if the distribution of x1 up to xn as x2, x3, and so on are coming from some symmetric distribution, like even a uniform distribution, then uh, this theorem may be valid even if n is less than 30. Even if n is 10, uh, the distribution of the standardized sample mean will be very close to the standard normal, even if n is equal to 10. So therefore, n is 30 is a good situation to look at in that or use in that kind of situations, right? So you have to be careful, therefore, when you apply the central limit theorem, don't take that n equal to 30 as a magic number where you can use in all situations. So that is an important thing to remember. So just to demonstrate you that the distribution of the standardized sample mean converges to the standard normal distribution as n is increased, I'm going to consider a parent distribution from which x1, x2, x3 are coming from. Uh, the exponential distribution with rate parameter zero point 0.1. So this is actually the density function of this distribution is very skewed like this. So I'm going to consider a skewed distribution as my parent distribution. X1, X2, X3, and my observations will come from this distribution. The mean of this distribution is 1 over 10, 1 over zero point 0.1, that is equal to 10. The standard deviation of this distribution is also the same number, right? So I'm going to sample from a distribution, right? So you can forget about the name of the distribution. That is how we apply the central limit theorem in applications of central limit theorem. We actually don't know the distribution from which our observations are coming from. But here for the demonstration, we have to generate some data. Therefore, we have to assume some distribution. So I'm just considering this skewed distribution to show that n equal to 30 even may not be enough, right? That was the objective of choosing this distribution. So let us take a random sample of size 5 and consider x bar 5 and then standardize that quantity and look at the distribution, right? So I'm I'm showing you the histograms and the smooth density curves of those histograms uh, in different situations. That means with different ends. So first situation, I'm taking samples of size 5 from this distribution. And then for each sample, I calculate the sample mean. In that case, it is x 5 bar. right? I'm considering x5 bar and then taking away the mean and then divide by the standard deviation. That is, I'm considering now Z5, Z5. So generate Z5 again and again and again by taking different samples from that distribution. And I have drawn the histogram of those different Z5 values. I have generated 10,000 Z5 values, and this is the histogram. And the smooth density curve is this blue one. And in order to show that actually in that case, it is quite different from the limiting distribution, the standard normal distribution. I have drawn the standard normal distribution in the graph in red, right? So you can see that when n is equal to 5, of course, uh, the sampling distribution of the standardized sample mean and the limiting distribution are quite different. This is the situation when the sample size is 10, right? So in this case, I am taking samples, sample of size 10, and then calculate the standardized sample mean is at 10 in that case. Is at 10, keep it, and then take another sample of size 10 and calculate is at 10, and like that, repeat it 10,000 times. So we'll have 10,000 is at 10 values, and this is the histogram of that. And blue curve shows you the approximate density function of that. And red curve shows the standard normal distribution. You can see that the blue curve is more close to the red standard normal distribution when n is equal to 10 than when n is equal to 5. But there is a quite big difference between those two. In the tails, they are different. In the middle also, they are different. And this is the situation when n is equal to 20. Right now, you can see that the 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 distribution of this Z20 is more close to the standard normal than the distribution of Z10 here. But still, there is a quite significant difference, right? Because the red curve is uh, somewhat to the right of the blue curve. They are quite different. Here, this is the situation. Even n is equal to 40. You can see that still they are quite different, right? And this is the situation when n is equal to 80, and this is the situation when n is equal to 86, 186. Sorry, 160, 160. Right. So you can see that when n is as large as 160, the two densities are almost the same. Of course, remember this blue curve is not the theoretical distribution here. Blue curve is the smooth histogram. So it is not the theoretical one, but it will be very close to the theoretical distribution because I'm generating this density using 10,000 values. So therefore, it will be very close to the theoretical one, but not exactly the same. So, but now in this situation, you can see that the red curve, which is the standard normal, and the blue curve approximate theoretical distribution of the standard Z 160 in this case, very close, right? So you can see that what I mentioned earlier, n equal to 30 or 40 is not a magic number. And if you use the distribution of this Z40 as the standard normal distribution, your conclusions or your mathematical probabilities that you calculate using that approximation uh, may be quite wrong, right? So therefore, you have to be careful when you are applying the central limit theorem. So as I mentioned, these blue curves are the approximate densities of Z5, Z10, Z20, Z40, Z80, and Z160, right? I can actually theoretically also derive the distribution of those quantities because I know that the x1 up to xn are coming from exponential point one distribution. So I derived the theoretical formula and I have drawn the theoretical densities, actual densities of Z5, Z10, Z20, and so on. And also I have drawn the standard normal curve. right? So this red curve here is the theoretical Z phi distribution. Theoretical distribution of Z phi. And then this one is the theoretical distribution of Z10. This one is the theoretical distribution of Z20. And the next one is the theoretical distribution of Z40. So you can see that even n is equal to 40. And this dotted line or the dashed line is actually the standard normal distribution. So when n is equal to 5, you can see that the theoretical distribution of Z5 and the standard normal distributions are quite different, right? Uh, you can see that it's converging to this one, coming close and close to the standard normal as n increases. But even if n is equal to 40, there is a slight significant difference, right? Because it's still in the middle here, right? And also in the tails. So especially when you are calculating quantiles or probabilities in the tail, using this approximation, you may make a significant error uh, if you assume that uh, the distribution of Z40 is approximately standard normal, right? But if I increase this further, it will be coming close and close to this one. But I didn't draw more lines here because then it will be very difficult to distinguish. So that's what I wanted to show. You can see that the density is coming more and more close to the standard normal distribution. So that's what the Central Limit Theorem says. The distribution of Zn converges to the standard normal as n goes to infinity. Right. So that is the convergence in distribution. It's called the weak convergence as well. Now we will look at the last type of convergence that we will be looking at in this lesson. Convergence in mean. When we talk about convergence in mean, actually we are considering convergence in mean uh, in several different powers. So therefore, just usually we call it LP convergence. LP convergence, where P is the power that we are going to consider. So this type of convergence focuses on average distance between yn and y. So up to now, earlier we were considering the distance between xn and yn and y between the random variables. How close the yn to y uh, as random variables in the first two types of convergences, almost sure, and then in probability. And then we looked at how close the distributions are in convergence in distribution. Now we are looking at how close the expected values are. So that's what we are going to look at, right? So the most common version of LP is L square, where P is 2, right? But in general, we say Yn, sequence of Yn converges to random variable Y in the LP sense if the expected value of the absolute difference of yn minus y to the power p approaches 0 as n goes to infinity. Of course, for this to be considered, expected value of yn to the power p, and thereby expected value of this quantity has to exist, right? So this can be considered only if that exists, right? So mathematically, we write it down like this, right? We say yn, sequence of random variables, yn converges to y in LP if the expected value of absolute yn minus y to the power p approaches 0 as n goes to infinity. That is the definition, right? So this is written as this: yn converges to y in LP mode. Okay. And I'm not going to look at examples of this thing. I'm just giving you as one more uh, to complete the types of convergence. right? So a special case is, as I mentioned earlier, is when P is equal to 2. In that case, we call it the mean square convergence. Mean square convergence. Yn converges to Y in mean, MS mean square, right? So mean square convergence is the convergence usually considered in forecasting and signal processing because it minimizes the variance, right? So you try to see whether the expected value of yn minus y square, which is actually the variance, when unbiasedness is there. Otherwise, it's called the mean square error, right? So whether that is converging to zero, right? Whether the variance is converging to zero or whether the mean square error is converging to zero as n goes to infinity. So that is what we usually check in forecasting, because when we forecast in long terms, we want uh, the variance or the mean square error to be getting smaller and smaller, right? As n goes to infinity. Right. Okay. So those are the different types of convergence. So finally, I'm going to just give you just a schematic diagram here showing implications. Sometimes one type of convergence implies another type of convergence, right? So as I mentioned earlier, the practically most strong or the practically strongest convergence type of convergence that we consider is the almost sure convergence, right? So I'm not going to prove any of these things. I'm just giving you this for the completion of the session or the lesson. Almost sure convergence implies convergence in probability. Convergence in probability implies convergence in distribution, that is the weak convergence. Right? And also LP convergence implies convergence in probability. So those are the implications between those. Almost sure convergence implies this one, therefore almost sure convergence automatically implies convergence in distribution also, right? So convergence in probability implies convergence in distribution as well. And then LP converges if P is greater than or equal to 1, of course. We don't usually consider negative P's here or 0. So convergence in LP implies convergence in probability. Uh, but not this one, actually, the implication goes the other way around also, but with some additional requirements. So therefore, I have just mentioned the requirement here for you to read. Uh, so remember this. So that's the end of this session. Now we have completed uh, the modes of stochastic convergence. We discussed several types of convergence, starting with everywhere convergence, which is not very practically useful to us. But then we discuss almost sure convergence, convergence in probability, convergence in distribution, and convergence in mean, right? I gave you some practical examples. Remember, we considered strong law of large numbers as a practical application of the almost sure convergence, and then weak law of large numbers as a practical use of convergence in probability, and then central limit theorem as a practical application of the convergence in distribution, right? So those are very useful uh, results. So that is the end of this lesson.